Hello everyone. Today we are talking about energy in fluids and specifically Bernoulli's equation. Bernoulli's equation. So Bernoulli's equation denotes the pressure and the energy of a fluid passing through a pipe. So right off the bat, you hear the phrase energy, we're thinking joules, energy in joules. And Bernoulli's equation is denoted by three parts that are held constant. So the energy within one part of the pipe, so let me do this in a better color, let's say red. The energy in one part of the pipe is equal to the energy in another part of a pipe. It's just that the specific type of energy, let's say like potential energy or kinetic energy, differs at these different points, and the pressure differs as well. So keeping this in mind, let's just break down this equation real quick. So when we're looking at this equation, we can kind of see that the parts resemble equations that we are very familiar with. So rho gh is very similar to mass times gravitational acceleration times height, which is potential energy. So we can say that this is some equivalent of a potential energy, with the difference being that instead of mass, we're now using rho, which is the density of the liquid. And for water, it would be 1,000 kilograms per meter cubed. 1,000 kilograms per meter cubed. And we see the second part here, 1/2 rho times velocity squared. That's very similar to kinetic energy. Kinetic energy, which is equal to 1/2 mass times velocity squared. So right away, we see that some equivalent of kinetic energy plus some equivalent of potential energy plus the pressure at a specific point is equal to the sum of the kinetic energy plus potential energy plus pressure at a different point. And it's also important to note that the direction of fluid motion denotes pressure change, because liquids flow from high pressure to low pressure. So with that in mind, as a liquid travels through a pipe, let's say that pipe is vertical and the cross-sectional area is held constant. If everything is held constant, the velocity and the potential energy, there's no change in that pressure. But as soon as we change, let's say, the cross-sectional area, then we're affecting the velocity. And as a result, affecting the pressure at different points within that pipe. So we have a couple examples going over this. I just wanted to give a brief overview of Bernoulli's principle, and with that, we can get started on the questions. So for 5-11, quiz question 1, we have an ideal fluid flows vertically upward through a uniform, constant radius, pipe, and the question is asking us to predict what would happen to the fluid speed and the fluid pressure. So this question is relying on two equations. The first one being the Bernoulli equation that we discussed up here, and the second one being the flow rate equation, where Q, the flow rate, is equal to the cross-sectional area times the velocity. And we know that at any specific point in a pipe, as long as there are no leaks or no additional channels or being like diverting the fluid, we know that the flow rate is constant at any specific point in that pipe, meaning that as long as there is no change in cross-sectional area in a pipe, the fluid flow rate, and by proxy the velocity of the fluid, does not change. So since this pipe in this problem has a constant radius, the cross-sectional area at any given point does not change. It is the same at point 1 or point 2 or point 3. So that means that the velocity of that fluid would not change. It would stay the same, which is why for this first part here, the stays the same is the answer, because according to this equation, as long as there is no changes in the amount of fluid, there's no changes in the cross-sectional area, then we won't see a change in velocity. Now, what we do see in the second part is a change in height. So we see a delta H. So I'm going to make this pipe look a little nicer now, remove some of the frailty. Oh, there we go. There it goes. I'm going to make it a little longer. So I'm going to also add a second line to denote a different height. So for the Bernoulli equation, we had stated that any change in energy within the system just converts from one form to another. So we know that the velocity and the density in this remain constant. So let me write out the Bernoulli equation one time down here. 1/2 rho v squared 1 plus rho gh 1 plus pressure 1 is equal to 1/2 rho v2 squared plus rho gh2 plus p2. So we know that the velocity and the density does not change given the Q equals AV equation that we had noted earlier. So we can effectively get rid of the kinetic energy portion because it remains constant throughout this situation. So let's just get rid of it. And let's consider the rho GH and the pressure at 0.1. So this is 0.1. And the rho GH and the pressure at 0.2. So this would be 0.2. So we know that the height at 0.2 is greater than the height at 0.1. So if the height at 0.2 is greater than the height at 0.1, that means that this portion of the Bernoulli equation right here is greater. It would be greater than this part right here. And since it's greater, we know that the sum of rho GH1 plus pressure 1 has to be equal to the sum of rho GH2 plus pressure 2. So if this portion here increases as it goes from point A to point B, so this would be point A, and this is point B, if rho GH increases, that means that the only other variable that could have changed is the pressure. So if rho GH increases, that means the pressure must decrease in order for this equation to remain constant. So let's just put in hypothetical values again, as usual. Let's say that rho GH is equal to 10 for some reason, times a pressure, or plus a pressure that's equal to 100. Well, if we increase a certain height to get to, let's say, the rho GH is equal to 50, however this multiplies out, it equals to 50. Well, we know that the sum of these two values has to equal 110. 110 has to equal 110. So solving for pressure, we would arbitrarily find that pressure would be equal to 60. And again, these are just arbitrary values to present the relationship between these values. But we see that as rho GH increases, the pressure decreases, which means that for this specific question, as the height increases, the pressure decreases. And that is why these two are the answers for this question. So for 5-11 quiz question 2, we see an ideal fluid flows through a pipe. Which of the following would most likely result in the greatest increase, in pressure within this fluid? So we're going to break this up into two parts because this question is asking us to consider two variables at the same time. So let's try and consider them separately and then consider the sum of the two parts together as when considering this whole problem. So the question is referring to both the radius of the pipe, so referring to Q equals A times V, and the height of the pipe, so the angle of the pipe. So we can say the rho GH of the pipe. Let me just erase some of this. So recall, if we increase the cross-sectional area of a pipe, we decrease the velocity of the pipe. And plugging this into the rho GH equation, if we held, or the Bernoulli equation, sorry, if we held the height constant, so let's say we have a pipe, and the only difference is that it gets skinnier, so the cross-sectional area decreases, but the velocity increases. If we plug this into the Bernoulli equation, where the height is held constant, so there's no change in the height, we see that 1/2 rho times velocity squared 1 plus pressure is equal to 1/2 rho velocity 2 squared plus pressure 2. And let's say that this is, let me do this in a different color. This is 0.1 and this is 0.2. We know that velocity here is greater, and we know that the overall energy within the system has to remain the same. So if velocity is greater at 0.2, that means that the kinetic energy portion of this equation is higher. So that means the pressure must be lower, as we exhibited in our last example, where increasing the height decreases the pressure. It's the same relationship here. Since we know that the sum of all the energies at point A is equal to the sum of all of energies at point B, then we know that as if the velocity were to increasing this this part of the Bernoulli equation, the pressure must decrease. So in order to then increase the pressure, because the question is asking for the greatest increase in pressure, we would have to decrease the velocity. And how do we decrease the velocity? Well, by increasing the cross-sectional area. We now have a greater cross-sectional area, meaning that according to the Q equals AV equation, as cross-sectional area increases, the velocity decreases. And if we were to compare 0.1 to 0.2, 0.2 has a lower velocity, which means that it must have a higher pressure. So we know that increasing the radius, as we exhibited through the Bernoulli equation and through the flow rate equation, we know that increasing the radius would result in an increase in pressure. So both C and D are false, because decreasing the radius would increase the velocity, which would in turn decrease the pressure. But now let's consider the second portion, which is highly related to this equation that we have here. So it's highly related here. So as we had just discussed, if we increase the height, so I'm going to just come back up here because it's already laid out for us. When we increase the height of the liquid, we're increasing the equivalent, like let's just consider this potential energy, the equivalent potential energy at point B compared to point A. If the potential energy increases, then the pressure must decrease, because the sum of all of these energies must be equal. So if this is higher, if this value right here is higher, then the pressure must be lower. So in order to have the highest pressure, we would have to decrease the height. So that means in order to have the greatest increase in pressure, we would want a decrease in height, a decrease in h, and a decrease in velocity, And which answer choice best represents this? Well, it's answer choice B, because if we were to just kind of draw this out, we have a pipe here, and it's angled downward suddenly, and it also gets bigger. So the cross-sectional area is greater, and its height is lower. So height is lower and velocity is lower. So as a result, the pressure must be higher in order for the Bernoulli equation to remain balanced. So that is why B is the answer. So jumping ahead here, because we went pretty in-depth with those last two examples about the relationship between these two, between the variables of the Bernoulli equation. So let's consider 5-11C. An ideal non-viscous incompressible fluid in a pipe of uniform width, so no change in velocity, flows up a hill with a height h, as shown here. What is true about the pressure of the fluid as it travels up the hill? So as we had stated, we're just going to consider the rho gh1 plus pressure 1 is equal to rho gh2 plus pressure 2. As the height increases, so this is point h2 and then this is h1. So as a height increases, we know that this quantity here is going to get higher. And in order for the sum of these two variables to be equal to the sum of these two variables, we know that the pressure must be lower. So P must decrease as height increases. And you may know this if you live in an apartment complex. I know my grandma lives on the 4th floor of an apartment complex, and the water pressure coming out of her shower is very weak. In a hotel, especially if you're on the 20th floor of a hotel, it's like I barely feel that water. So keeping that in mind, we know that as height increases, the pressure decreases, which would correspond with answer choice A, as we have noted multiple times throughout this lecture today so far. So that is why A is the answer, because as height increases, this quantity here for increases as well, and in order to remain constant with the initial situation at point A, the pressure must decrease. So that is why A is the answer. Okay, so moving back up to 5-11A. An ideal liquid with no viscosity and is incompressible flows from left to right through this horizontal pipe whose interior is hidden. At which point does the pipe have the smallest inner diameter? And then it states that a higher fluid level in the vertical pipe indicates a higher pressure inside the horizontal pipe. So this question already is correlating pressure to diameter. And what do we remember about diameter? Well, it's directly related to Q equals A cross-sectional area A times V, the velocity. So pulling up the Bernoulli equation one more time, we know that at least within the horizontal pipe, the height is not changing. So let's only consider 1/2 rho V squared 1 plus pressure 1 equals 1/2 rho V squared 2 plus pressure 2, okay? So, as we stated, in a higher fluid in the vertical pipe indicates a higher pressure. So if let's compare point C to point B. If the pressure is higher at point C, compared to point B, let me erase the arrow here. So if pressure is higher here at point C compared to point B, that must mean if pressure is higher, according to this equation, for these units to be equal to one another, this pressure must be lower, right? Because the ideal liquid is not as high, which means that the velocity must be higher. So the velocity is lower at this point, at point C, than it is at point B, because the pressure is greater. And we can then relate that to the flow rate, which would then mean that with a low velocity, point C would have the greatest diameter because it has the highest liquid height. So we can begin to make an image of what's happening here. So in a different color, let me do this in red. We can say that maybe at point B we have a very narrow pipe, that the fluid is moving very fast, so it has a very low pressure, but it has a very small cross-sectional area. And the question is asking us about the diameter. So it has the very small cross-sectional area, which would mean it has a very small diameter. And then as it gets to point C, the cross-sectional area increases, which leads to a lower velocity, and a greater pressure, which is denoted both by this equation and by the height of this the liquid in this vertical pipe. Now let's go back to point A. Well, point A has a higher liquid. The liquid in the vertical height is higher at point A than it is at point B, which must mean that the pressure is higher at point A than it is at point B. So pressure is lower at point B compared to point A, which would then mean that the velocity at point B is greater than the velocity at point A. So relatively speaking, as we move from point A to point B, the velocity increases, but the pressure decreases. So if velocity increases from point A to point B, that must mean that, according to the flow rate equation, the cross-sectional area would decrease, which would then mean that the diameter of that tube decreased as well. So we can kind of draw a sort of middle-sized pipe here. So if we were to compare the relative diameters of the pipe at each of these locations, A, B, and C, we see that because the pressure is greatest at point C, it would have the greatest cross-sectional area. In contrast, because the pressure is so low at point B, it has the lowest cross-sectional area and it has the highest velocity. And since it has the lowest cross-sectional area, that means it has the lowest diameter, because the equation for the cross-sectional area of a circle would be A equals pi r squared. And if area is smaller, then the radius must be smaller. So with all this information in mind, we can then see that B is the answer because pressure is lowest, which means that velocity is highest. And since velocity is highest, and we know that flow rate stays the same, then that must mean that the cross-sectional area has decreased, which results in point B having the smallest inner diameter. And that is why B is the answer. So let's move on to our final problem. So for our final problem, we have 5-11b. And 5-11b says, an ideal non-viscous incompressible fluid in a pipe of uniform width flows up a hill of height h as shown. The moving block slides up an identical hill. What is true about the motion of the fluid and the block as they travel up the hill? Okay, so as we've been stating throughout this lecture, for the flow of a liquid, we know that the flow rate is equal to the cross-sectional area times the velocity. So even if the height increases for the liquid, even if it's increasing in its potential energy, as long as the cross-sectional area of the pipe it's in remains the same, which it is in this question with the phrase a pipe of uniform width, as long as the cross-sectional area remains the same, the velocity is going to remain the same. So this means that for a fluid flowing up a hill, the velocity is not going to change, but what is likely changing is the pressure. So the pressure is changing, as we have stated throughout this lecture. As we increase height, pressure decreases. So we know that for the liquid flowing up the hill, the velocity is not going to change because it's in a pipe of uniform width, which would mean that the flow rate remains the same. Now, in contrast, let's compare it to the block. The block doesn't have this flow rate property. When we're considering the energy of the block, we consider the potential energy, so mass plus the kinetic energy. So potential energy would be mass times gravitational acceleration times height, plus the kinetic energy is 1/2 mass times velocity squared. And that would be equal to the mass times the gravitational acceleration times the height at point 2, plus the mass 1/2 times the mass times the velocity squared at point 2. So if if the energy within this system over here is to remain the same, then as height increases, I'm going to do this in a different color, as height increases, the velocity must decrease in order for these two sides of the equation from point 1 to point 2 to remain the same. So if this side of the equation were to equal 10,000 joules, for example, we know that the sum of these two quantities, the potential energy and the kinetic energy at point 2, point 2 must be equal to 10,000 joules. So with that being said, if the height were to increase, the only variable that we could change within this system, or the only variable that would change, is the velocity. The velocity would decrease. So with that being said, we know that for fluids, the velocity is the same. But for a block, the velocity decreases. And when we look at the answer choices, answer choice A says that both the fluid and the block slow down. Well, the fluid would only slow down if the cross-sectional area of the pipe increased, which it's not, because as we stated, the pipe is of uniform width. So this answer choice is wrong. It says the block slows down, but the fluid speeds up. The fluid would only speed up if the cross-sectional area decreases. So since the cross-sectional area is unchanging, this answer choice is false. C says the block slows down, but the fluid speed stays the same. That is correct. That is what we've shown through our analysis of the flow rate equation and of the conservation of energy equation. So C is correct. But let's go through the last two choices. D says the speed of both the fluid and the block stay the same. Well, that's not true. As we have seen, that would only be the case if the block was traveling across a horizontal surface with no height increase and there was no friction. So if there was 1, no friction, and 2, no height change, then there would not be a change in the velocity or the kinetic energy. But since we do have a height change, we have a decrease in the kinetic energy as it's being converted into potential energy, meaning that the velocity is now lower at point 2. So that is why D is false. And E says the block speed stays the same, but the fluid slows down. Well, as we have shown, the fluid is not slowing down because the cross-sectional area is staying constant, which means the velocity is staying constant, and the speed of the block is decreasing, as we have explained numerous times. So that is why E is false. And that is the last question for this set. Hopefully you enjoyed this video. If you did, please give it a like, and have a great day.